4.5 billion years ago, the ground beneath us was not solid rock, but a churning, screaming ocean of liquid fire. This was the Hadean Aeon, a name fittingly derived from the Greek underworld, Hades. To look upon Earth in its infancy would be to witness a scene of absolute geological violence. The planet was a blazing sphere of molten slag, spinning wildly through the debris field of a chaotic young solar system. There were no continents, no oceans, and certainly no life, only a toxic, roiling surface constantly pulverized by asteroids the size of mountain ranges. To the modern eye, this world would be unrecognizable, a vision of hell suspended in space. The atmosphere was a suffocating, lethal shroud, a reducing mixture of carbon dioxide, methane, ammonia, and hydrogen sulfide. If you were to stand on a cooling raft of basalt in that era, the atmospheric pressure alone would crush you, and a single breath would incinerate your lungs. There was no free oxygen. The element we associate so intimately with vitality was locked away in mineral structures or bound in scalding water vapor. The sky was not blue, but likely a bruised shade of dull orange or red, scattering light through a haze of hydrocarbon smog. And from this sky, death rained down with terrifying frequency. During the late heavy bombardment, roughly 4.1 to 3.8 billion years ago, the Earth was hammered by the leftovers of planetary formation, vaporizing any primitive crust that attempted to harden and resetting the surface again and again. Yet, in this inferno, a miracle of chemistry began to unfold. As the bombardment slowed and the planet radiated its heat into the vacuum, the surface temperature finally dropped below the boiling point of water. But where did the water come from on a world born of fire? Modern planetary science suggests a dual origin: icy comets raining down from the outer solar system, and perhaps, more significantly, the Earth exhaling. As the magma oceans cooled, massive volcanoes spewed gigatons of steam into the atmosphere. This vapor condensed, triggering a deluge that may have lasted for centuries. A global storm that drowned the fire and birthed the primordial oceans. These were not the blue oceans of today. They were likely green with dissolved iron or black with depth, hot, acidic, and treacherous. But they offered something the surface could not: protection. It is here, in the crushing darkness of the abyss, that the greatest mystery in the universe unfolded. Somewhere around 3.8 billion years ago, the boundary between dead matter and living biology was crossed. We know this because the Earth remembers. In the ancient sedimentary rocks of Isua, Greenland, and parts of Canada, geologists have unearthed a ghost: distinct carbon signatures. These are not fossils of bones or shells, but chemical shadows, an unusual ratio of carbon-12 to carbon-13 isotopes that nature alone rarely produces. This fractionation is the fingerprint of life, suggesting that even in the chaotic transition from the Hadean to the Archean Aeon, something was metabolizing. Something was alive. But how does a chaotic chemical soup become a self-replicating machine? The prevailing scientific consensus points away from the sunlit surface, which was bathed in lethal ultraviolet radiation due to the complete absence of an ozone layer. Instead, we look to the deep. Deep-sea hydrothermal vents, specifically alkaline vents, provided the perfect incubator. Here, seawater seeped into the fractured crust, reacted with the hot mantle rocks through a process known as serpentinization, and erupted back into the ocean as superheated, mineral-rich fluids. These vents acted as natural chemical reactors. They created steep gradients of temperature and acidity, generating a flow of electrons, a natural battery. In these microscopic pores of rock, complex organic molecules could concentrate and organize. It was not life as we know it, but prebiotic chemistry. The RNA world hypothesis suggests that before DNA and proteins took over, RNA molecules ruled. These versatile strands could perform two functions simultaneously, storing genetic information like a hard drive and catalyzing chemical reactions like an engine. It was a fragile, molecular dance occurring in total darkness, fueled not by the sun, but by the chemical energy of the earth itself. The first entities to emerge from this chemical cradle were single-celled organisms, the ancestors of bacteria and archaea. These were extremophiles, the hardiest survivors imaginable. They did not breathe oxygen. Instead, they breathed rock and gas, extracting energy by oxidizing hydrogen, sulfur, or iron. They were slow, anaerobic metabolizers, living in a world of silence and crushing pressure. To them, oxygen would have been a deadly poison, a highly reactive gas that tore organic molecules apart. One of the most profound pieces of evidence for this early struggle comes from stromatolites. These are not creatures, but cathedrals built by creatures. Dating back 3.5 billion years, these layered, rock-like structures were formed by mats of sticky microbes trapping sediment, grain by grain, layer by layer. In places like Shark Bay, Australia, living stromatolites still exist today, direct descendants of the earliest colonization of our planet. They represent the first time life did not just exist in the environment, but began to physically shape it. This was the state of the Earth for over 1 billion years, a microbial world invisible to the naked eye. The oceans were teeming with microscopic life, yet the planet appeared dead from space. It was a time of evolutionary stagnation, so where the primary goal was simply to maintain the integrity of the cell against a hostile universe. The water acted as a shield, blocking the ultraviolet radiation that scorched the barren continents. Life was a prisoner of the ocean, huddled around volcanic vents or clinging to the shallow seafloors, waiting for an innovation that would change everything. It is humbling to realize that for nearly half of Earth's history, we were nothing more than slime on a rock. There were no eyes to see the stars, no ears to hear the crashing waves, and no brains to wonder why. There was only the relentless, blind imperative of chemistry: replicate, survive, repeat. But deep within the genetic code of these primitive organisms, a ticking clock was set. Evolution is rarely static. The pressure to find new energy sources was mounting. The stage was set for the single most destructive and creative event in planetary history. Life had conquered the dark, but it was about to discover the light. A specific group of bacteria was on the verge of unlocking a technology that would turn the sun itself into fuel, and in doing so, they would unleash a waste product so reactive, so toxic, and so powerful that it would wipe out nearly everything on Earth before paving the way for the complex world we know today. The era of the fire was over. The era of the great oxidation was about to begin. Around 2.7 billion years ago, the Earth's trajectory was forever altered by a microscopic biological machine. In the warm, iron-rich oceans, a new type of organism began to proliferate: cyanobacteria. These were not the passive scavengers of the deep. They were innovators, and they had evolved the ability to tap into the most abundant energy source in the solar system: sunlight. Through photosynthesis, they split water molecules to harvest energy, releasing a waste product that the planet had never truly dealt with before: molecular oxygen. To the modern mind, oxygen is synonymous with life, but to the anaerobic organisms that had ruled Earth for over 1 billion years, oxygen was a weapon of mass destruction. It was highly reactive, stripping electrons from essential biological molecules and dismantling the machinery of life. As cyanobacteria bloomed, they pumped this corrosive gas into the oceans, triggering the first and perhaps most significant mass extinction in Earth's history. The ancient, anaerobic masters of the world died in the trillions, their lineages extinguished by the very element that would one day sustain us. The evidence of this planetary chemical warfare is etched into the bedrock of the Earth itself. As oxygen flooded the seas, it reacted with dissolved iron, causing it to rust and settle onto the ocean floor in vast, red layers. These banded iron formations, which we mine today for steel, are the rust of a dying world, a geological tombstone marking the moment the oceans oxidized. But the devastation did not stop at the water's edge. As oxygen escaped into the atmosphere, it reacted with methane, a potent greenhouse gas that had been keeping the Earth warm under a faint young sun. As the methane was destroyed, the planet's thermal blanket was ripped away. Temperatures plummeted. The Earth entered a terrifying feedback loop known as the cryogenian period. Ice sheets expanded from the poles, reflecting more sunlight into space, which cooled the planet further, driving the ice even closer to the equator. For millions of years, Earth became a snowball, a white, frozen sphere encased in ice up to a kilometer thick. The hydrological cycle slowed to a crawl. The oceans were sealed off from the atmosphere, choking the carbon cycle. From space, the planet would have appeared utterly dead, a silent, frozen wasteland drifting through the void. Yet life is tenacious. Beneath the crushing weight of the global glaciers, in the pitch-black waters warmed by volcanic vents, pockets of microbial life held on. They waited in the dark as the geological clock ticked forward. The thaw, when it finally came, was violent. Volcanic activity, unchecked by the ice, slowly pumped carbon dioxide back into the atmosphere. With no rainfall to wash the CO2 out, the greenhouse effect returned with a vengeance. The ice retreated rapidly, unleashing a torrent of nutrient-rich meltwater into the oceans. Phosphates, minerals, and oxygen flooded the seas, creating a chemical cocktail that would fuel the single greatest burst of evolutionary creativity the world has ever seen. Around 541 million years ago, the fuse was lit. The Cambrian explosion was not a gradual climb. It was a biological detonation. In a geological blink of an eye, mere tens of millions of years, life diversified into nearly every major animal body plan known today. The oceans, once dominated by simple mats and soft-bodied grazers, became a chaotic arena of complex, multicellular life. This was the dawn of the arms race. For the first time, evolution began to favor armor and weaponry. Organisms stopped relying solely on chemistry and started building machines. They extracted minerals from the water to construct hard shells, spines, and exoskeletons. The trilobite, with its segmented armor and complex eyes, became the icon of this new world. And indeed, the invention of the eye changed the rules of existence forever. Before the Cambrian, life was blind, stumbling in the dark. Now, suddenly, there were predators that could see their prey. The hunter and the hunted emerged. Creatures like Anomalocaris, a bizarre, shrimp-like apex predator, prowled the seas, driving the evolution of speed, camouflage, and defense. The fossil beds of the Burgess Shale reveal a period of wild experimentation. Creatures with 5 eyes, asymmetrical bodies, and feeding appendages unlike anything alive today. Nature was throwing everything at the wall to see what stuck. Many of these biological experiments failed and went extinct, but the blueprints for modern life were drawn in these ancient, crowded seas. While the oceans churned with this new complexity, the continents remained barren rock, scoured by wind and radiation. But the oxygen revolution had one final gift to bestow. As oxygen accumulated in the upper atmosphere, it formed a protective layer of ozone. This invisible shield absorbed the sun's lethal ultraviolet radiation, finally making the dry land habitable. The colonization of land was not an event, but a siege. Around 470 million years ago, the first pioneers arrived, simple, moss-like plants that clung to the water's edge. They had no roots, no wood, and no leaves, yet they accomplished a feat of planetary engineering. They broke down the rock, creating the first soils and pumping even more oxygen into the air. They paved the way for the animals. Arthropods were the first to follow. Scorpions and millipedes crawled out of the water, pre-adapted with their hard exoskeletons, which helped retain moisture and support their bodies against gravity. But it was in the Carboniferous period that the oxygen levels truly reshaped the world. With atmospheric oxygen soaring to an estimated 35%, far higher than today's 21%, the biological limits on size were shattered. This was the age of giants. In the vast, swampy forests that would one day become our coal reserves, insects grew to nightmarish proportions. Meganeura, a griffinfly resembling a dragonfly, now patrolled the air with a wingspan of nearly 2.5 feet. Arthropleura, a millipede-like creature, slithered through the undergrowth at lengths of over 8 feet. Their respiratory systems, dependent on passive diffusion, could only support such massive bodies because of the oxygen-rich atmosphere. Meanwhile, a quieter revolution was happening in the shallow waters. A lineage of fish had begun to evolve fleshy, lobed fins and primitive lungs. These were not yet land animals, but they were caught in the transition. Creatures like Tiktaalik represent the bridge. Animals that could push themselves up in the shallows, gulping air. Over millions of years, these fins evolved into legs, and the first tetrapods hauled themselves onto the mud. They were amphibians, creatures of two worlds, tied to the water for reproduction but eager to exploit the resources of the land. They were the ancestors of all reptiles, birds, and mammals. But their foothold was precarious. The earth is never still. The climate was about to shift again. The continents were drifting together to form the supercontinent Pangaea, and the conditions that supported the age of giants were beginning to unravel. The stage was set for the rise of the reptiles, but the transition would be neither smooth nor peaceful. The Permian period loomed on the horizon, bringing with it a catastrophe so complete, so devastating, that it would nearly erase the experiment of complex life altogether. The oxygen that had built giants would soon be choked off, and the world would burn once more. The story of life is not a steady, triumphant ascent. It is a narrative punctuated by catastrophe. 252 million years ago, the Earth faced its darkest hour. This was the end Permian extinction, known grimly to science as the Great Dying. It was not a sudden event, but a slow, suffocating apocalypse. Massive volcanic eruptions in what is now Siberia, the Siberian Traps, ignited vast coal seams, releasing trillions of tons of carbon dioxide and methane into the atmosphere. The planet fevered. The oceans turned acidic and anoxic, transforming into stagnant pools of pink, bacteria-ridden water. In the blink of a geological eye, 96% of marine species and 70% of terrestrial life vanished. The biological hard drive of the planet was nearly wiped clean. But in the silence of the post-apocalyptic world, a specific lineage of survivors began to stir. These were the reptiles. Unlike their amphibian predecessors, they possessed a revolutionary biotechnology, the amniotic egg. With this watertight, self-contained life support system, they were no longer tethered to the water for reproduction. They could venture into the arid, punishing interiors of the supercontinent Pangaea. As the world healed, these reptiles diversified with terrifying speed, giving rise to the most successful dynasty the planet has ever known: the dinosaurs. For 160 million years, dinosaurs were not merely the inhabitants of Earth. They were its architects. They filled every ecological niche. They grew to sizes that defy modern physics, engineered by evolution to be efficient biological machines. They weathered drifting continents, shifting climates, and rising sea levels. And their dominance was so absolute, so complete, that it seemed they would rule forever. But the universe is indifferent to biological success. 66 million years ago, a random trajectory in the dark cold of space intersected with Earth's orbit. An asteroid, roughly 10 kilometers wide, slammed into the Yucatan Peninsula with the force of billions of atomic bombs. The impact did not just kill, it erased. In seconds, the asteroid vaporized, sending a plume of superheated rock and glass into the atmosphere. As this debris rained back down, the friction turned the sky into a broiler, igniting global forest fires that consumed the continents. But the fire was only the beginning. The true killer was the darkness. Dust, soot, and sulfur aerosols choked the upper atmosphere, blocking the sun for months, perhaps years. Photosynthesis stopped. The food web, anchored by plants, collapsed from the bottom up. The herbivores starved, and the carnivores followed. The dinosaurs, specialized for a world of abundance and warmth, found themselves trapped in a world of scarcity and freezing cold. In a geological instant, the masters of the planet were extinguished. Yet, in the freezing darkness of the impact winter, something moved in the undergrowth. They were small, furry, and unassuming. They were the mammals. For millions of years, they had lived in the ecological shadow of the giants, nocturnal and terrified, keeping their bodies small and their senses sharp. This marginalization became their salvation. Their small size meant they required less caloric intake. Their fur kept them warm in the cooling world. Their diet was flexible: insects, roots, and decaying matter. Anything that the dying world provided. With the dinosaurs gone, the Earth was a vacuum waiting to be filled. The Cenozoic era, the age of mammals, had begun. It was an explosion of form and function. Within 10 million years, mammals transformed from shrew-like scavengers into giants of their own. Whales returned to the oceans to become the largest animals in history. Bats conquered the skies. Massive herbivores roamed the expanding grasslands. But among these diversifying lineages, one group of tree-dwelling mammals, the primates, began a unique experiment. Around 7 million years ago, in the shifting landscapes of Africa, the forests began to recede, replaced by open savannas. A specific lineage of apes found themselves at a crossroads: stay in the shrinking trees or descend into the dangerous grass. They chose the ground. To survive, they stood up. Bipedalism was a profound adaptation. It freed the hands for carrying food and tools, and it raised the eyes to scan the horizon for predators. But it came with a heavy price. To survive in this complex, hostile environment, the pressure on the brain increased. Over millions of years, the human brain tripled in size. This was not an obvious evolutionary advantage. The brain is a metabolic furnace. In modern humans, it consumes 20% of the body's energy while representing only 2% of its weight. For a species living on the edge of starvation, this was a dangerous gamble. It required a longer childhood, more intense parental care, and complex social structures to ensure survival. Yet, this gamble paid off. We did not evolve sharp claws or thick armor. When we evolved the ability to remember the past and simulate the future, we learned to manipulate the environment, to control fire, to craft tools, and eventually, to tell stories. We became the first species capable of asking why. Looking back at this 4.5 billion year odyssey, one fact becomes terrifyingly clear. We are an accident. Our existence is not the inevitable climax of a grand plan, but the fragile result of a chaotic chain of events. If the early Earth had not been bombarded by icy comets, there would be no oceans. If the cyanobacteria had not poisoned the world with oxygen, complex cells would never have formed. If the asteroid had arrived 30 minutes later, it might have landed in the deep ocean, sparing the dinosaurs and leaving mammals as eternal underdogs, scurrying in the dark. We are the ghosts of the unlived possibilities. We are here because of the freezing hell of the SnowBall Earth, the suffocating heat of the Permian extinction, and the cataclysmic violence of the Chicxulub impact. Every mass extinction, every geological upheaval, was a filter that our ancestors miraculously passed through. Today, we stand as the inheritors of this legacy. We are the only species that knows its own history. We can read the diaries written in stone, the banded iron formations, the iridium layer from the asteroid, the fossilized bones of creatures that ruled for millions of years and then vanished. These records are not just scientific data, they are a warning. The Earth is not a static stage. It is a dynamic, often violent system that cares nothing for the life it sustains. The ecosystems we rely on, the stable climate, the oxygen-rich air, the biodiversity of the oceans, are not guaranteed. They are delicate balances achieved over eons of trial and error. To understand prehistoric Earth is to understand the fragility of our own moment in time. We are the first species with the power to trigger a mass extinction, and the first with the wisdom to prevent one. As we look backward into the deep time of magma oceans and green skies, we are really looking into a mirror. The survival of life has always been a game of adaptation and chance, but for the first time in 4 billion years, the future of the planet is not being decided by blind chemistry or random asteroids. It is being decided by us.